So, hi everyone. Hello. We're going to start the last contributor session of the day. So our first speaker is Marcelo Augusto Pinto from University of Palermo. And he's going to talk about the mission of giant atoms under an electric field.
Thank you very much. Thank you, the organizer, for letting me to present my work here in the conference. So today I'm going to talk about the work that we did at the University of Palermo, where we studied the behavior of the atomic population and the emitted field of normal atoms and giant atoms when they are coupled to photonic lattices with the presence of an electric field. So most of the results that I'm showing here will be about a 1D array that we have this preprint on the archive in case someone is interested. And if I have time, I'm going to show you also some preliminary results on what we did on a graphene-like structure. So let's do some review on photonic lattices. Every time I'm talking about lattices here, you need to think that I'm talking about lattices made of cavities. So a photonic lattice is basically a bunch of cavity that you put in a structured way. So if you put an emitter on, let's say, in this cavity, and the emitter is on the excited state, and you let it decay, the photon can hop from one cavity to the other with a hopping rate J. And for this type of lattice, we can write the Hamiltonian in this way, where the A and A dagger are the bosonic annihilator and creation operators. So we're going to work always on the first excitation sector, so it's just a single photon dynamics. And when you do that, the Hamiltonian simplifies to a simple tight binding Hamiltonian. And this is what we're going to use for our simulations that we're going to see. So to model the atom, we're going to consider a two-level system with a ground state and excited state and a transition frequency omega naught. And this two-level system will couple to our lattice can couple in two different ways. One of them is a local coupling, where the atom couples just to a single site on our lattice with a strength G. And can have a non-local coupling, where it couples to more than one site. Here I'm putting two, but can be more than two. And since they're non-local, we have a phase difference between the coupling points. And we are also working on the weak coupling regime. That means that G is much less than J, the hopping rate. So let's do a quick review on the 1D couple cavity array. So this is a simple textbook example. You should be familiar with that. So if we consider this 1D lattice, and we can solve it analytically, and you can find the dispersion relation is this cosine shape, and the eigenstates is just a combination of plane waves. Okay, so if we couple the atom, let's say in the middle of the band here, and putting it coupled to the middle of the lattice, we can express this Hamiltonian in this way, where the first term accounts for the atom degree of freedom, and the second part, the lattice, and the third, the interaction between the atom and the lattice. So if we look now to the emission of this emitter, here on this left plot, I'm plotting on the y-axis the position of the sites, and on the x-axis, I'm plotting the time. Our emitter here on the center of the lattice, and you can see as the time goes by, the probability that we find a photon is like the photon is propagating away from the emitter. And if we look at the atomic population, it decays exponentially with a decay rate G squared over J. So now let's see what happens if we add an electric field for this system. We can create this electric field by just adding a gradient on the cavity frequencies, and by adding this, this term on the Hamiltonian, this linear potential. And if you do this, we have like a constant field pointing on this direction on the lattice. And just by doing that, the properties of the lattices change a lot. Now the dispersion relation is not anymore that cosine shape, is features discrete levels, the Wannier-Stark ladder, and where each level is far apart by a distance f, that where f is our field strength here. So the eigenstate of these lattices is also very different. We have now something that is a combination of Bessel functions, and the eigenstates are localized with a localization length 2j over f that depend also with the field strength. So, well, as you can see, since f control the distance between the levels, f will define two different regimes in our lattice. So we can have a strong field regime when the qubit, our emitters see the discrete levels, and we can have a weak field regime where our emitter still sees discrete levels, but the levels are too close that he sees like a quasi-continuum, right? So let's see now the emission dynamics in each one of these with these regimes. So if we start with the weak field, here I'm plotting the qubit population, and the inset is the earlier times of the emission. You can see that, like in the case without the field, we have an exponential decay, but at some point we start to see revivals on the dynamics. This happens because if you look at the emission, the emitted field, we have now this oscillatory behavior that is called block oscillations. As you can see, the photon that is emitted here from the center of the lattice goes until, let's say, this 2000, this position 2000, and then goes back. And when it goes back to the emitter, we see a revival here. And this periodicity is very well defined. Also depends on f is TB. As you can see, I'm normalizing the time by TB. That is the block period. And you can see that the revival happens here on this first column for half integers of TB. But yeah, if we change now the frequency where the atom is resonant with, and for not being the center of the spectrum, now we translate it a little bit, we see that the times that these revivals appear is a little bit different. You can see that that happens because the photon that goes from one direction, let's say this one, travel a smaller path compared to this one that goes to the bottom part. Okay, and the other regime that you can look is the strong field, right? The strong field, we have like a Jaynes-Cumming-like interaction. You can see that I'm plotting here for three frequencies of the qubit. You can see for all of them we have the perfect Rabi oscillations. And since even having this type of Jaynes-Cumming interaction, you can see that the cool thing is we have a bunch of cavities happen being populated when we are on this regime. And another thing is I'm always keeping the qubit here on at the center of the lattice, but just tuning the frequency, we can change this bound state. You can move it around. For example, here is resonant for -3f. You can see that is a little bit translated downwards, and here is 3f. We can move it upward. Okay, so let's go back now to the case of the weak field. For this case and for the qubit on the middle of the spectrum, we can write a delay differential equation, and since it have this form, and we can see here the non-Markovianity of the system, where here the first term here depends only on t, but the other terms depend of earlier times, t minus integers multiple of tb or half integers of tb. And this is another interesting thing that we found is, if you look at the literature, we can draw a similarity of this system with a multimode cavity. For example, here from this paper from the late 80s, we can see that they found a very similar delay differential equation where they have an atom emitting inside of a Fabry-Perot cavity. So it's like our system is creating effective mirrors inside of the lattice. Okay, so let's change a little bit the topic and talk very quickly what we did on the 2D case. For the 2D case, now we're consider a giant atom. It couples to two different places of the lattice. And now we're considering photonic graphene. Graphene have two types of sites of the unit cell, on side of the unit cell. And it features two bands. So you can see that this bands touches at some specific points, and these points are inside of a region in the K-space that's called valleys. And you can see that we have 6 of them, but it's possible to show that only 2 of them are independent. So the idea here was to play around with the phase with this giant atom to make the emitted photon decouple from one of those specific valleys. And we managed to find this solution. If we set, for example, if N1 and N2 are the position of the legs, if we settle this phase and M is just an integer, we can make the photon, the emitted photon decouple from one of the, for the K valley, and this one for the decoupling for the K prime. Plugging some values, putting the one leg on the origin and the other one in the neighboring unit cell, we find that the phase is plus or minus pi/3. So here are some simulations. You can see here is a normal atom emitting. All the valleys are populated, and when we plug the phases, we can select specific valleys where the photon will couple. So the idea here, we also introduce a non-vanishing Berry curvature. We add the tuning between the sides A and B, and then this will make a gap open on the lattice, and then we have this non-vanishing Berry curvature, which is given by this value that is perpendicular to the plane of the lattice and have opposite signs depending of the valley, right? So the idea here is to play with the velocity of the photon, where we're going to make this quantity the anomalous velocity that depends of the cross product of the electric field and the Berry curvature be more preeminent than this standard velocity, and we try to see the current emission or lattice. So just for a normal atom, we introduce also a frequency gradient to create the electric field, and the normal atom couples to both valleys at the same time. You can see that the atom here, I'm plotting the lattice on, this is the positions, and the atom is here on the middle. You can see that it emits to perpendicular to electric field to both directions. But if we consider now the giant atom with the special phases that we derived, we can see that we can select the direction of the emission depending on the phase that we choose. So this is our collaborator, this is my advisor, Francesco Ciccarello, and this is a fellow PhD student, Gianluca, and this is Daniele, that is on the TNR Florence. And so just to conclude, what I'm showing you today is for the electric field on 1D system creates a non-Markovian behavior due to the presence of block oscillations. We create this kind of synthetic mirrors on our lattice, and for the graphene structure, it's possible to control the directionality of the emission by just playing with the phase of the giant atom. So thank you very much.
Any questions? No one? Don't be shy. Okay, so I have a bit of questions. The first one is that you're assuming in the first case an infinite change of atoms, and that, well, can you get into some details? Because I mean to assume that the resonance energy of each atom, no, increase with the site. So I mean, my question is that if you assume an infinite lattice of atoms, your atom, I mean, the very far atom is going to need to have a huge resonant energy, no? Or what numbers are you?
Yes, in theory, yes, but as we showed that the dynamics is confined and there is a localization. So due to the block oscillations, even if you have an infinite lattice, where is it? No. Okay. No. Sorry. Oh, sorry. Even if you have an infinite lattice, all the dynamics is confined nearby of the qubit that lies here on the center. So we have this distance here is 2 psi that depends on the electric field strength. Yes, yes.
Any more questions? Okay.
Hi, Marcel. First of all, thanks a lot for your presentation. I thought it was very nice. Now I'm looking at this graph here on the left, and I'm curious because it seems to me like the photons are bouncing back and forth, and it seems like you get a dynamic, periodical dynamics. However, the revivals have some sort of random values, like it experiences strong revivals and then small revivals. Do you know why this is? And thank you.
Well, in this case, I mean, it's a behavior that's very hard to explain, because when the atom comes back, some part of the light are absorbed and give rise to the revival, and some parts are just reflected. And as you can see on the second, that we don't have the symmetry on the emission. Some parts are reflected and some parts are transmitted. So maybe this play a role on this, but it's this behavior of not being the same size. I think that's very hard to describe.
So, if there are not any questions, let's thank the speaker again, please. So, one of the speakers is Rodrigo Grande de Diego, is going to talk about squeeze lacing via cavity-assisted Raman transitions.
Okay, so thank you for the introduction and for allowing me to talk in this nice conference. And yes, I'm going to talk about the squeeze lasers, which are basically quantum light sources that combine the spectral purity of lasers with the reduced quadrature fluctuations of squeeze states. So let me just very briefly begin by reviewing these two aspects. So we know that we can represent every quantum state in the phase space with its Wigner function. And in the case of vacuum, well, we obtain this Gaussian-like shape. And we can apply operations to this state. For example, we can displace it, okay? So we get this coherent state. And you see here that the fluctuations of vacuum are the ones precisely that minimize the Heisenberg uncertainty relationship. So we can also apply another operator to this state, that is this squeezing operator. And when doing so, what we get is that in a given quadrature, we get a reduction of the fluctuations by a factor R. So this is squeezing, just having fluctuations in a quadrature below the vacuum one. And now let's see how can we describe quantum mechanically a standard laser. So we're going to start by having obviously a cavity. Inside this cavity, I'm going to have a gain medium. In my case, it's going to be a minimal gain medium, a two-level system, and these two elements are gonna interact. So I add this James coming term to the Hamiltonian, and then I'm going to add some incoherent processes, in particular photon decay and pumping of the qubit for having lacing, and these appear in the master equation as Invariant terms. So I can get this equation and make a mean field prediction, a mean field derivation, just ignoring the quantum fluctuations. And what I encounter is that the laser exhibits a driven dissipative phase transition in which I enter in a regime of stimulated emission whenever a control parameter called cooperativity surpasses a threshold value. And well, so yes, I have a macroscopic photonic population in this regime, and the light emitted in this regime has a ring-shaped Wigner function in this steady state, which is just a mixture of coherent states for every value of the phase. I have obviously a very narrow peaked emission spectrum. This is just the monochromaticity of lasers. And I have no photonic correlation, so my photons are independent. And these are, this is a summary of the main properties of lacing. And why do I want to include the squeezing among these properties? Well, it turns out that a squeeze vacuum is normally prepared by using these optical parametric oscillators, which display also a driven dissipative phase transition very similar to the one of lacing, in which we also have a regime of stimulated emission. The problem is that we cannot benefit from the narrow band emission spectrum from this regime in this case, because as you see here in the animation, we just get a squeezing below the threshold value, okay? When we penetrate within this regime, the squeezing is degraded and I get a mixture of two coherent states. So this is the problem. It is difficult in general to generate narrow band quadrature squeeze light. And here is where the squeeze laser could be a possible solution, okay? That could have applications in fields like quantum metrology and quantum sensing, for example. And well, this concept was originally proposed in the microwave by some colleagues from here in the IFF. And the first optical implementation was proposed back in 2021 by my supervisor, Carlos Sánchez Muñoz. And today I'm going to talk about a new implementation we are working now, also in the optical. But first, let me just talk about the key idea about these implementations. Well, we normally work with a basis of focus states, but we can actually apply a squeezing operator to these focus states and work in a basis of a squeezed focus states like this, okay? And in this basis, well, this is just equivalent to applying this Bogoliubov transformation. And here I will have, well, these annihilation operators in this basis, okay? So what's the goal? The goal is to implement a standard lacing, not in the bare basis, but in this squeeze basis. And in this way, I will get my squeeze lacing back in the bare basis. So let's see what happens when we do this. Let's assume I have achieved my goal. I have a James Cummings Hamiltonian in the squeeze basis. And let's undo the squeezing transformation. Let's get back to the bare basis, where I obtain this Hamiltonian that you may identify with the asymmetric or generalized Rabi Hamiltonian, okay? Which is a Rabi Hamiltonian, but with different coupling strengths for the co-rotating and the rotating and the counter-rotating terms. So let's just add incoherent processes to this Hamiltonian, photon decay, pumping of the qubit, even spontaneous emission. And what I get from the mean field derivation is that there exist two regions of lacing over here, okay? Well, let's see how is the light emitted in these regions. Well, for example, if I place myself here when no counter-rotating terms are present, I get a standard lacing. But if I move upwards in the y-axis, I start getting a squeezing. So this is my squeeze lacing. In the normal phase regions, I get just a squeeze vacuum or vacuum if I don't have counter-rotating terms. And how is the light in this region, in these lacing regions? Well, within the lacing regime, I get the line narrowing typical of lasers, and photon correlations now are not photons are not independent anymore, but now there is a certain bunching effect in the lacing regime that indicates that now in my squeeze laser photons are correlated. And let me just finish by briefly talking about this atomic implementation that I have mentioned before. So I will be using for these rubidium-87 atoms, which are the favorite atoms of quantum opticians, and I will be focusing on the D-line transition, which is this optical transition over here. So we know that when considering the nuclear spin, this transforms into a 4-level system, and here I will have my effective qubit over here, okay, and formed by these 2 ground states, and then I will have these other 2 excited states that I will call S and R. So I will place this atom inside an optical cavity, and this cavity is going to induce transitions in my atom. For example, I can look at this transition over here, okay, and then using a laser I can induce this other transition. So I am creating a way to go from level 0 to level 1. And what am I essentially doing? This is a resonant Raman transition, and what I am essentially doing is adding an excitation to my effective qubit by absorbing a photon from the cavity. So I am basically describing this term in the effective Hamiltonian. The inverse path would describe this other term, and I can, in the same fashion, include another Raman transition for the counter-rotating terms, okay? And well, when I eliminate formally, I can eliminate adiabatically the R and S levels from the complete Hamiltonian of the system, and what I obtain is precisely the generalized Rabi model. That's what I wanted, okay? So let's see how this model behaves when adding the pumping and adding the photon decay. I will also add, for completeness, all the dissipative processes that takes place inside the atom. And I will just solve the master equation, and this is what I got for the photonic population. Okay, so just above this black line, which marks the mean field lacing threshold, so above this line I would expect having lacing in my effective model. I get an enhanced photonic population in the parameters space, and just for getting a better understanding of what is happening, I'm going to use as figure of merit the second order coherence function, which is this quantity over here that will be 1 whenever photons are independent. And I know that in my squeeze basis I have a standard lacing, so I'm going to compute this quantity in order to find the lacing regions. And what I see is that indeed there is a big lacing region for this model in which I will have a squeeze lacing in the bare cavity mode. So this would be it. I just want to put these final take-home messages, just the definition of a squeeze laser, the fact that we have implemented it using these Raman transitions in multi-level atoms, and finally its potential applications in quantum metrology. So with that, thank you for your attention.
Okay, so any questions? Okay.
Okay, thank you, Rodrigo, for a very clear talk, very nice. I have a question because you need this Hamiltonian where you have a Rabi model or James-Cohen model, but instead of classical Fock-state operators of creation and destruction, you have Bogoliubov modes, no? If I understood correctly. So I didn't quite understand how you create the specific so you need a Hamiltonian with a specific superposition of annihilation and creation that is exactly the Bogoliubov mode. How do you create this Hamiltonian? Maybe I didn't start well.
Okay. Well, the thing is that in this implementation, from one side, this Bogoliubov mode that you talk about, this superposition, naturally appears. I mean, if you have this asymmetric Rabi model, for this, that I have here, okay, here, it is simply, for example, you take this constant here,
and this other one, and you can reparameterize it just by call it g times an hyperbolic cosine of or an hyperbolic sine, and in the end with the 4 terms. Okay, so you will have here also the Hermitian conjugate. You get exactly the transformation that you need. It is what I have. What I tried to explain here in this here. Okay, so here I am just substituting this expression here in this expression, and you get the Rabi model.
So, okay.
Hi, thanks for the talk. I'm just wondering that, okay, so you described the idea of a squeezed state, but it's not clear to me how this squeezed lasing is different from, for example, like a strongly driven spontaneous parametric down conversion, or what you get out of it. Could you say a little bit about that, please?
You mean the optical, for example, an optical parametric oscillator, for example, or a standard lasing, or
no,
because I mean, in the down conversion, you can actually implement also squeeze lacing using down conversion, and it's actually what Carlos did in the paper that I showed at the beginning. But you have to be careful of for example, eliminating noise and things like that, because if not, normally with down conversion, I think that what happens is that you can end up with this mixture of coherent states, you know, in the stimulated emission regime. I think that's what normally happens. For example, the decay model, for example, also features this type of states. So I don't know if that's what you refer to or not.
Maybe we can talk about it later. But
Okay.
thank you anyway.
Okay, so if there's not any questions, more questions, let's please send the speaker again. So our next speaker is Julio Sánchez Cánovas, and he's going to talk about the collective relative effects in atomic ensembles.
Thank you. Good afternoon, everyone. Thank you for having me at this conference, and thank you for being here. I'm going to talk about collective radiative effects in atomic ensembles. And first of all, we can ask ourselves, why should we study this kind of systems? And the main reason, if we think in an application, is that this kind of systems, under certain circumstances, they show large coherent times. So they are potentially useful for applying quantum protocols on them, okay? So first of all, if we study the collective emission in atomic ensembles, we can find two different situations. First of all, if we have an atomic ensemble and the atoms are not interacting between each other strongly, the interaction is weak, we can find that the intensity of the emission, the spontaneous emission, is proportional to the number of atoms. But under certain circumstances, if these atoms are strongly interacting, we can find that the intensity of the emission is proportional to the n squared of the atoms. And also, in other circumstances, the emission can vanish totally. This is known as superradiance and subradiance, respectively. Okay? So the first guy that studied these problems was Dicke, with the famous Dicke model of the seminar paper of 1954. And he described these systems, atomic ensembles, as a system of coupled spins. And his description of spontaneous emission was a sequential photon emission through symmetrical states from a maximum excited state to the ground state. And he could reach to the description of the qualitative superradiance. But this model has some limitations. First of all, this model doesn't allow us to prepare the initial state. We are not describing absorption of photons with this model. And also, this model just led us to describe single photon emission processes. We cannot emit 2 or 3 photons at a time. And there's no description of photonic states. There's just description of spin states. So for overcoming with these difficulties, we are going to propose a model that has into account the entangle of the photonic states and atomic states. And we are going to formulate a Hamiltonian that takes into account the Hamiltonian of the atoms, the Hamiltonian of the field, and the coupling between these two. And we are going to study the collective absorption and emission of photons in terms of probabilities. Okay, so we are going to start to describe our model. Our model consisting in atoms in I positions coupled with the electromagnetic field through the electric dipole approximation. And we are going to consider that these atoms are 4-level systems, 1 ground system and 3 excited atoms, 3 excited levels, sorry, n minus, n, and n plus, which is a typical configuration of Rydberg atoms. Okay. And we are going to describe the following interaction. We are going to consider that our initial state, the system is totally unexcited. All the atoms are in the ground state. And this ensemble is excited by a pulse of Rabi frequency omega L, resonant with the transition G to the excited state N. And the duration of this pulse is much less than the atomic lifetimes. This is just to avoid repopulation phenomena. Okay? And we are after this pulse, we are going to disconnect the laser, and we are going to study the collective spontaneous emission of the system. And we are going to use a wave formalism, and we are going to use the time evolution operator, which is the time order exponential of the time integral of the Hamiltonian of the system. And we are going to look for a time-independent effective Hamiltonian, which accounts for the electromagnetic interaction still order 4 in W. Okay? And we are going to include the laser interaction with the atoms, the interactions between the atoms, the interatomic interaction, and the incoherent process of decay that happen in this system. So first of all, we are going to consider the interaction of the laser with the atoms, and we are going to consider that in the pulse, while the pulse is activated, or while the laser is activated, the atoms are driven by the laser in a strong coupling regime. So the absorption and emission of photons is led by this laser, and we can describe this coupling with this Hamiltonian in terms of the Rabi frequency of the laser. Then we are going to consider the interatomic interactions. And we have 2 kinds of interatomic interactions. First, we have the dipole-dipole interaction, which describes the resonant energy transfer between an excited atom and a ground atom. And in the near field, we can approximate this interaction to the C3 interaction term that is widely used in the literature. And then we are going to consider the van der Waals interaction between atoms that are in the excited state N. And in the near field approximation, or in the near field, we can approximate this to the C6 interaction term. Okay. As I am using quantum electrodynamics formalism, I'm expressing these interactions in terms of the green function of the electric field, but it's nothing else. Okay, and finally, in this Hamiltonian, we are going to introduce also the decay, the incoherent time evolution of the atomic states due to the spontaneous emission of single atoms. And just for this, we are going to introduce a imaginary shift in the Hamiltonian of the atoms, okay? So after all this process that requires some calculations, we find an effective Hamiltonian which takes into account all these interactions, and this allows us to express or to formulate to calculate a time evolution, an effective time evolution operator, which can be expressed in terms of the eigenvalues and eigenvectors of this effective Hamiltonian. And using these eigenvalues, which are a function of these characteristic interactions, we are going to describe the properties of the collective absorption and collective emission. First, we are going to talk about collective absorption, and we are going to talk specifically about a system of two atoms. We find that under some circumstances, when the atoms are interacting, the system cannot absorb photons. And this is called absorption blockade, and there are two kinds of mechanisms. First, a dipole-dipole blockade, which is due to the dipole-dipole interaction, and then a van der Waals blockade, which is due to the van der Waals interaction. And we find that a dipole-dipole interaction takes place in any kind of photon absorption, but the van der Waals blockade just takes place when the system is already excited. Okay, so if we have that the interatomic interaction is much larger than the Rabi frequency of the system, the probability of absorption tends to 0. Okay, so and this is known as blockade of the absorption. And then, in the case of collective emission, just to describe very simply the phenomena that we get with this model, is that there are two kinds of emission processes: single or free space emissions, which are depicted here in the left side, in which just one atom is involved. But additionally to this, we have a second kind of emission, that is emission by interference, where at least two atoms are involved. And these processes are the processes that make the system to be superradiance or subradiance. Okay, and this process of decay by interference, making some calculations, we can find that there's also a blockade of these channels. And this is due to the breaking of the degeneracy made by the van der Waals interaction. And this reduces the total probability of emission. We can compute the number of channels, the numbers of ways of decaying, and it depends on the number of atoms and the number of excitations that the system has absorbed. And in the particular case of having one excitation, we find that the number of channels is n to the square, which is the result that Dickey had in his model. Okay, for finishing the talk, we can describe more in detail the emission, the process of emission of a two atom system. Using the effective Hamiltonian that has this shape, making the calculations of the eigenvalues and eigenvectors, we can express the effective Hamilton, effective time evolution operator, and we can study the spontaneous emission process of an initial state in which both atoms are excited. And here we find two kinds of emission processes. Processes where just one photon is emitted, and processes where two photons at a time are emitted. Okay, and we find the processes where we have emission in free space and the emission by interference. And we find the following result. We can compute the probability of not emitting one photon or two photons. And we find the following, that if we have in the left side, if we have two atoms separately, asymptotically, we reach that the probability of emitting two photons is 1. And in short times, we have a maximum probability of emitting one photon. But if we put the atoms very close together, we find that the probability of emitting one photon R2 tends to 1/2. So it shows that the cooperative phenomena enlarge the coherence times of the system due to the dipole-dipole interaction. Okay, and in any time we can demonstrate that the sum of the probability of not emitting one photon or two is equal to 1, so this preserves unitarity. Okay, so I finish my talk with some conclusions that you have there, and just telling you that with this model, as a further future work, we are trying to simulate system of a higher number of atoms, such as 10, and for that we need computational methods. Okay, thank you for your attention.
Any questions?
Thank you for your talk. It was very nice. I have a question regarding interactions between the dipoles. So, like, as far as I remember, like the interaction basically depend on orientation of dipoles. How did you initialize the orientation, and do they change during dynamics, or like, or are they fixed?
Yes, of course. Yes, it's a very nice question, and in fact, the dynamics change completely with the initial orientation. Yes. And the easiest way is trying to create an axis with an electric field, an electrostatic electric field, and try to initialize the dipoles with that direction. Also, as an approximation and just to play with the model, you can consider isotropic dipoles. But it's true that you have to fix clearly the initial conditions that change totally the dynamics. Yes.
So in your case, they were all aligned in one direction?
For this, I consider isotropic for these computations in the two atom system. Yes.
Thank you.
Thank you very much for the talk. I didn't really understand like the fact that dipole-dipole interactions and coherent and incoherent and collective decay can allow processes of subradiance is a known result. Like there is a lot of literature about this, and I don't really understand what is the new thing. And second thing, what you call van der Waals interaction is also what is commonly known in literature as Rydberg blockade, or it has any difference? Thank you.
Okay, I start with the second question. Rydberg blockade is the blockade of absorption due to van der Waals. But van der Waals, when I talk about van der Waals, I mean the interaction. And when I talk about blockade, is having zero probability of absorbing photons. Okay. And related to the first question, what do you mean that you don't understand I mean, I didn't understand properly your first question. What do you mean about the superradiance or subradiance? Can you repeat, please? Yes.
Can allow for with coherent and incoherent dipole interactions allows for subradiance. I didn't quite understand like.
Yes.
Point,
Okay.
yeah.
So look, okay. Here we have incoherent interactions and or incoherent time evolution and coherent time evolution. Incoherent time evolution are processes that reduce and do not conserve probability. For example, spontaneous decay. Here we have the natural decay of the atoms, or also the decay due to the transfer of photons that I put here in this process, these two. It's true that these two processes are incoherent, but when you have the dipole-dipole interaction, you have a transfer of the initial excitation between atoms. There's a periodic transfer of the excitation. So in that interaction is coherent because it doesn't lose probability. The system doesn't lose probability.
Okay, thank you very much for your nice talk.
Okay, so let's thank the speaker again, please. Okay, so our last speaker of the day is Maxim Lendev, and he's going to talk about spatially resolved photon statistics of general nanophotonic systems. So, Maxim.
Thank you, Blas, for kind introduction, and thank you, organizing committee, for having me here. So, today I would like to present my recent work, which is entitled Spatially Resolved Photon Statistics of General Nanophotonic Systems. Let me start with a bit of introduction / motivation. So, as you may know, the generation of non-classical light is attracting a lot of attention in the field of quantum optics, and examples of those states can be different, such as entangled states, squeezed states, or single photon states. And all these examples hold a huge potential for quantum technologies, for example, in secure communication, high precision sensing, and quantum computing. As a promising platform for generating those exotic states of light, like there is so-called light matter interfaces, and they usually consist of some quantum emitter embedded into some cavity, and then the basic idea is basically by classical driving, you can, and by engineering the interaction between quantum emitter and the modes of your cavity, you can manipulate the properties of the light which is being emitted from the system. So once this light is emitted, it is also important to properly characterize it. So like for this, experimentalists usually use this object which is called electric field correlations. So the first order correlation function carries information about intensity of light, which one can detect at any point of space. And the second order correlation function basically gives us information about statistical properties of photons. And it is standardly used in quantum optics in order to distinguish, for example, single photon emission from coherent emission or thermal emission. So light matter interface is one of the topic of my talk. Let me stop a bit on it. So let me consider a simple example of it. So we have quantum emitter embedded into Fabry-Perot cavity, and this Fabry-Perot cavity has very nice properties. Its mode structure is very easy in the sense that the modes, they are equidistant in frequency space, and also all these modes, they have very small losses usually. So we basically can easily quantize light in such a cavity, and then the dynamics of the whole hybrid system can be easily reproduced using this Rabi Hamiltonian. And once you know Hamiltonian, you can get any observables you need, emitter dynamics, electric field correlations, or whatever else. And like the most important term here is the third one, which means interaction, and it is proportional to the coupling strength. And as you can see, coupling strength is inversely proportional to square root of mode volume. And this basically tells us that like cavities with a huge mode volume won't allow us to have huge enhancement of interaction. That's why Fabry-Perot cavity is probably not the best candidate to manipulate properties of light. That's why people started to look more into nanophotonic setups, where it is possible to create modes with very huge localization of light. And it actually allows for very huge interactions. However, like the light pattern, like let's say field has very complex properties in such cavities, and usually modes of these cavities, they have huge material losses, which doesn't allow us to straightforwardly quantize light in such system and describe dynamics, and so we don't have straightforward access to observables we would like to have. This, however, is not fully true in the sense that like there are like methods which allow to quantize light in such systems. And for example, this framework of macroscopic quantum electrodynamics, in the end of the day, it shows us that light-matter interaction in such systems can be described using this type of Hamiltonian. It's very actually similar to the one I showed you. Like the only difference that now instead of single mode of the cavity, we have photonic continuum, and this photonic continuum interact, all these modes of this photonic continuum interact with quantum emitter. And then formally you basically solve your problem. You have access to emitter dynamics and electric field correlations. However, it's only a formal solution in the sense that practically it's very difficult to treat photonic continuum. So we need to find some other way to achieve, to get our observables. So like, and for this, let me take a look at this, the third term, which is interaction, and like the coupling can be expressed in terms of so-called spectral density. Like this is like quantity from classical electromagnetism, and can be computed using standard classical electromagnetic solvers like COMSOL or whatever. And usually it says it tells us information about modes supported by now our nanoparticle or whatever nanostructure. For example, these peaks, they basically tell us that there are kind of 3 modes in our system. And so the thing that like this quantity spectral density is indeed key quantity here for us because it fully characterizes the action of cavity on emitters. And let me show you in the next slide how we are going to use this fact to simplify our problem. So as I showed you before, the Hamiltonian of light-matter interaction can be written in this way, very like this cloud of harmonic oscillators basically represents a photonic continuum. And the idea is basically to replace this cloud with something else which is easy to treat and at the same time which has the same action on quantum emitters. And like what we choose, we use like set of few lossy interacting modes which we will show is absolutely equivalent to this original complex electromagnetic environment. So these modes, they are able to interact between each other, they are able to lose their energy into environments, and they are also able to couple to quantum emitter, and then the corresponding Hamiltonian is this. So how we are going to find the equivalence between this model and this model? Yeah, like this is a question, and it turns out that for this new model which we introduced, it is possible to find expression for effective spectral density, and in terms of parameters of this model, in terms of frequencies, couplings, and losses. And then the idea would be just to fit this spectral density to the original spectral density of our environment, and basically this allows us to find the parameters of the systems of the model. And then when we have parameters, we basically are able to calculate dynamics and whatever else. However, like these new modes, they basically contain information about real electromagnetic field, only the positions of emitter. So they basically, we know that they basically introduce the same action on emitter, but overall the properties of them are not the same as of real electromagnetic field, and we don't have basically information about electromagnetic field in any other position. Let me show how we are going to overcome this issue. So like for this, we are going to introduce detectors explicitly into our setup, and these detectors we are going to model as just weakly coupled two-level systems. If you then do algebra, you will see that actually population operator of these two-level systems which we introduced is proportional to intensity operator in this specific location where we introduce these two-level systems. And then it basically means that these two-level systems, they basically count photons in their respective positions. Like important thing here is that they should be weakly coupled, so they don't introduce any back action to our original system, and they only probe system without affecting it. So in the end of the day, basically we treat our detectors as additional emitters, and now our field detection problem is reduced to interaction of multiple emitters with the field, which we already know how to solve. I hope I told you about this at the last slide. And so now we basically have access to everything we need. Let me show how I'm going to calculate the electric field correlations. So we consider this setup. So it basically has, it is nanoparticle, silver nanoparticle, and we are going to see how field in presence of this nanoparticle interacts with quantum emitters. So let me first characterize the modes of this nanoparticle. We're going to see in far field, like we have in frequency space, we have clearly two peaks, and these two peaks correspond to two different modes. And if we look at the radiation pattern, so basically how this mode radiate into far field, like at which angles they radiate, whatever, we see that they are absolutely different depending on the frequency. And now the idea is that we are setting our emitters in resonance with one of the modes, and then with another mode, and let's see what we are going to get in our detection setup. So as you can see, like if we set our emitters in resonance with this mode, we get exactly like radiation pattern which is similar to what we see in classical case. And if we put our emitters in resonance with this one, we have exactly 3 peaks, what you would expect from classical simulation. So nothing really crazy, which makes sense. So basically reproduced our classical result. However, with our model, we can now go to not only to intensity, but also to statistics. And let me calculate G2, which is a measure of photon statistics. And as you can see, like with these red plots, we see that photon statistics really depends a lot on where you detect your photons. So for example, in these points, we have G2, which is very close to 0. It basically means that if you detect at these specific locations, you will have a single photon emission. If you detect in this specific location, you will have a very huge probability of photon pairs. And the same we have for another adjustment when our emitters are in resonance with another mode. And it basically tells us that already for this simple system, we have very non-trivial behavior of photon statistic depending on angle of where we're going to detect. And in the end, let me say some conclusions. So I presented to you a method which provides an access to the photon correlation resolved in space, frequency, time, and polarization. We show that already for simple geometries, light statistics is very non-trivial, and these results enable design of novel non-classical light sources which can exploit quantum light matter interactions at the nanoscale. In the end, also let me tell that this paper relied on these results has recently been published in PRX Quantum. We studied way more than I showed you here, so please, if you're interested, take a look. And also would like to acknowledge my collaborators, especially my supervisors, Francisco Jose Garcia Vidal, Johannes Feist, and I would like to thank you for your attention.
Okay, so any questions?
So I think I got a bit confused when you were saying at the beginning that you could solve the dynamics of this problem by mapping it to just a few modes that have some Lindblad dynamics. Is this general, or do you have to impose some conditions on the coupling and whatnot?
Well, in principle, it is quite general, and for example, we can treat strong coupling like regime of light matter interaction with this. The only assumption is basically that your original state of your environment should be Gaussian. So you cannot start, for example, with some Fock state in your
in your electromagnetic environment. And but in principle, yes, the only approximation is that we do fitting, and then if you don't do fitting well, you introduce some kind of problems. But in principle, it's general, yes.
But you would need like for an arbitrary spectral density, you would need like an arbitrary number of modes, an arbitrary number of couplings.
Yeah, in principle, like complexity of spectral density introduces like some you will need to introduce like more modes in order to kind of to fit everything. You would need more fitting parameters to fit like more complex spectral density, and that would mean that you will have in your quantum dynamics like more modes.
So what is a bit confusing is that in principle, by having like this linear combination of damped modes, you are restricting effectively to having some Lindblad dynamics, right?
Yeah, in principle, yeah, they have Lindblad losses indeed, but how to say, in the end of the day, what matters is only spectral density. If you assuming that your environment is originally in Gaussian state, the only thing which matters is spectral density, and basically emitter interacts with spectral density. It doesn't know anything about modes unless you are in non-Gaussian state.
But there must be something apart from this Gaussianity, right? Because I mean, I can think about like the environment even being in the vacuum state, and if there are like non-Markovian evolutions that do not.
Yeah, I mean, it is fully represented. Like you can treat non-Markovian dynamics using this method. The original papers, like of my supervisors, where they propose this method, they treat strong coupling. Like I also treated at some point ultra strong coupling. There is also paper in PRL, and yeah, we perfectly reproduce the exact dynamics where we just basically discretize the continuum. And it's basically we get the same results.
Okay, very interesting. Thank you.
Thank you.
Okay. Any last question? No? If no, let's thank the speaker again, please. And now going to have the poster session, but I have to remind you that you have to check your poster with yours at the end of the poster session, okay?